Okay. Ever since I was a kid, I've been obsessed with exotic visual media. And recently, I saw a video of the Action Lab covering the endotrope. And I was instantly hooked. So I went to binge watch all the videos made by the inventor of the endotrope, Mike Endo. And I decided I just had to build one. Now, before we start, I think it's best I explain what an endotrope is and how it achieves this almost hologram-like effect. This is a zoetrope.
Dear God.
There's more.
No.
It's an invention from 1866 to create moving pictures. This was before the film projector was invented. And an endotrope is just a zoetrope, but instead of a bunch of static images, you use two screens. So I've actually pulled a classic tech bro scam and I've reinvented 200-year-old technology and called this new and groundbreaking, serious cutting-edge science, right? If you want a more in-depth explanation, I will link the video of the Action Lab in the description. I think he's an excellent science communicator and he can explain how an endotrope works a lot better than I can explain it. And while you're down there, I would really appreciate it if you would like and subscribe, because this is just the beginning of our little endotrope adventure. So while my predecessors opted to use phones or tablets as their screens, I chose to design a fully integrated PCB with screens, because I thought it would be more cost effective and less resources demanding, right? Even though I still ended up sinking a whole lot of cash into this project, but regardless of what my mother thinks of my spending habits, I think it was definitely worth it. Then I started designing the PCB with all the features I could possibly need and, could cram into it really.
Alright, here we are in KiCad and this is the blueprint for my latest PCB. This is where the RP240 should be connected to, right? I opted to solder the microcontroller directly to these pads instead of integrating it into the PCB because it saved me quite a hassle. This is a ribbon cable connector for the screens. The screens are driven over SPI, which is connected right here. It's just one wire where all the data flows through, which isn't really optimal to drive screens that way. However, it's quite easy and it's quite convenient, so we'll do it that way. This is where the SD card should be inserted in, right? Here you can see an SD card, basically. And I didn't connect it through the SPI bus. Almost always SD cards are also connected over SPI to a microcontroller, but this would also go through that one wire and add extra latency to my screens, which I really don't want. So I connected it directly to the RP240 through the SDIO protocol, and I am certain this won't come back to bite us later. Then here is the charging circuit. It accepts the incoming voltage from the RP240 and sends it in a controlled manner to our battery. I hope at least. And here is the Hall effect sensor. There's also one located right here, and it's just to tell me which screens are where. It's a magnet sensor. I'll put a magnet on the assembly and then I'll know when to draw the frames to the screens.
And with that, I ordered my PCBs and then I started soldering. Bad news everyone, I was gonna start soldering, but then I realized I didn't have my 1 microfarad capacitors because I forgot to order them. They weren't in my shipping list from DigiKey, which means I'll have to order them again. They're worth around 16 cents, but the delivery cost will be around 13 euros, which I find ridiculous. So I hope I've forgotten other things, so it's not that ridiculous. When I tested my PCBs, the screens just wouldn't work, and after some troubleshooting, emphasis on trouble, I found out that the wiring to the ribbon connectors was reversed. So I had to fix that in my PCB design software, and I had to reorder my PCBs. And then my new PCBs arrived, and I started soldering again, and again the screens wouldn't work. But this time I tracked it down to a very likely short I caused, soldering the teeny tiny ribbon cable connectors to the PCB. This is to be expected when soldering SMD components by hand. SMD in this case standing for Surface Mount Device. But it could also stand for Suck My Dick, the way I suffer soldering these. That is until my 20th birthday, where I got this bad boy. This is a digital microscope specifically for soldering, and it cleared up a lot of the pains I've been having soldering using a dinky magnifying glass from my dead grandmother. With this hurdle over one, I gave it another shot and got closer and closer and closer to soldering the ribbon cable connector to the PCB without any shorts. But every time I was sure there weren't any shorts, I measured it, I ran some tests, and I started to solder the rest of the PCB to it. And then I plugged it in, and then it would go completely haywire and short out again. And every time the short would be with the ribbon cable connectors. And at this point I was even running out of spare parts, and I had to steal them from previous failed PCBs. And let me tell you, desoldering a 1/4 millimeter by 1/2 millimeter components by hand, even with the microscope, is a real pain in my ass. But eventually, thanks to some divine miracle, I managed to create a PCB which didn't have any shorts in it. So it's finally time to test if everything works.
Quick update, we're 5 months ahead. I didn't get to work on it like before this week, and I've been working at it since because of schoolwork, tons of schoolwork. I had my exams or finals, whatever, study engineering, so I passed them, but I still have to redo exams, like second chances from the previous semester, because I was a lot less motivated, so to speak, back then. Anyways, the redesigned PCB arrived. It works now, right? It works now. So it works now. Would you look at that? That works. The magnetic sensor, that also works. I tested the battery. That seems to work. I hope it works. The screens work now. The only thing that doesn't work is the SD card. So basically there are two main ways that I figured out you can use an SD card using a microcontroller. The first way is through SPI, which is the same protocol and even the same wire that the displays use. So you'll have to cram a lot more data through the same wire, which made me opt for the second way, which is SDIO, which is just connecting it straight to the PCB and not like an intermediate thingy, which would seem a lot faster. The problem is that the RP240, which I use when I'm using a knockoff, that doesn't support it. I found one library that seems to be able to read raw data, so not like files or anything, from the SD card, but that's in Rust, and I don't know what the fuck Rust is. I don't know how to write in Rust, so we'll have to make do with the 2 megabytes of onboard flash storage, which we'll see.
So if anybody of you guys watching is like a super genius, go write in SDIO library in C for the RP240. Pretty please. So for the time being, we're stuck with the 2 megabytes of onboard memory of the RP240. But at least I did manage to get the screens and the magnet sensor to work perfectly. Now at this point in our story, I went to watch the new Superman movie. But accidentally, I booked a 3D screening. However, thanks to that mistake, I had an epiphany.
So I made a breakthrough. You see, I recently went to watch Superman in the cinema, and by chance, accidentally, we selected a 3D movie which works with these 3D glasses. Now these aren't the blue and red glasses you might expect. These are polarized glasses which work by projecting 2 types of light onto the cinema screen. One type is for the left eye, one type is for the right eye, and these polarization filters, they filter out the light. Now I'm going to show you something. The light of the screen is going through the first pair of glasses and it's getting polarized. Then it goes to the second pair of glasses, and because they are in the same orientation, it lets it through. But if I twist it, look at that, it just turns black, which has huge implications for this project. All other endotropes in existence, which I know of 2 of them, there exist 2 other endotropes, they just use a black box around the screens, which means that the final image is floating in a black box and not like a real hologram, which would be floating in, well, in real space, which would be partially see-through. And I think using these polarization filters, we would be able to create a more realistic, well, more cool see-through effects, which I hope. Well, the middle part will still be no black bar, but we'll see. I'll have to order some polarization filters, and I'll be working on the 3D model of the enclosure. So I'll see you when that's done.
So I figured out how to make the endotrope see-through, which is crazy. It's the closest thing we can make that is like a high resolution hologram. There exists like very, very low blocky holograms of like spilling LED matrices. But yeah, that's crazy. All other endotropes that exist right now still use completely black opaque shutters to block out the light. But if we use polarized film, we can create shutters that are see-through for all other light except for the light coming from the screens. Hola, die weg. Where were we? All other endotropes that exist right now effectively use black shutters to block out the screen, resulting in the hologram floating in a sort of black box. However, if we utilize polarized film, we can ensure that the light from the environment can pass through the endotrope freely. However, the light from the screens can be blocked, effectively creating shutters that only work for the screen. Mike Ando did mention using privacy film to create a see-through effect. However, I think using polarized film is a much more controllable way to achieve this effect. Now it's time to design a housing for our PCB, the screens and the motor that will spin the entire thing.
I was in an entranced like focus state for 2 days, and I 3D modeled the 3D printed parts for the endotrope. So here are the results right now. I learned this program in those 2 days, or maybe 3 days, I don't know. Time has lost all meaning to me. So it's FreeCAD, I learned it. It's free and it's open source, so I can't complain, but it's very buggy. I recommend everyone to check it out so it gains more popularity and more support online for the issues I've been facing. It spins. I've managed to make it spin, so that's great. This is I've ordered these, And I'll see you when they arrive, I suppose.
After some rushed 3D modeling, I ordered the parts and waited for their arrival.
This is the one and only golden Labubu. No, it's not. It's a cardboard box of my 3D prints. It's finally arrived. It was a real hassle getting it. Because apparently I wasn't home when they tried to deliver it while I was home. And I don't think I just think that they just drove by and took a picture of my front yard, because that's what the delivery service showed as proof that I wasn't home. A picture of my front yard, our front yard. I mean, my parents' front yard, whatever. But I got it now, and I'm slightly worried because this looks like it has been dropped. That's package material. That's great. Okay, that's great already, but that's not the thing I'm the most worried about. Oh, look at that. Completely intact. That is amazing. I hope nothing identifiable was flashed on camera. Right there. This is amazing. This is great. This is great news. Look at that. It is beautiful, quite frankly. I am proud of myself. It's designed by me, 3D printed by some guy in Germany, by some company, and I think they subcontracted it because I didn't order it from Mr. 3D Schmidt, but apparently on the box it said it came from Mr. 3D Schmidt. So yeah. Beautiful. I'll see you when I put this together now, and I'll see you then. And I'd like to wish an apology for the state of my hair.
Now I could finally start to assemble the thing, which, truthfully speaking, was another pain in my ass.
I look even worse than before. We can't really talk that loud because it's 12:15, 12:15 midnight even, and this is where we're at. I've managed to glue one polarization filter on it. The issue with the polarizing filters is that there's a sticky side, but it's not sticky enough to stick to the 3D print. So it gets all gross. I left this one out too long and it's just really gross.
When I tried to attach the polarized film, it just wouldn't stick to the screen holder I designed. I tried using double-sided tape, I tried using the sticky side of the polarized film, I even tried super glue. But nothing worked, it just wouldn't stick. And at this point, the frustration and the glue fumes were getting to my head.
I'm losing my mind! I'm trying to glue the polarized film onto my film holder and screen holder, basically. The issue is this does have a sticky side which seems to stick to everything except the 3D print. I've tried super glue, which seems to stick to everything except the polarized film. I really don't have any more options left except for just zip tying it, I guess. But the issue is that I don't have any zip ties.
So I just bit the bullet and bought zip ties. Now at this point we were ready for our first test run.
It kind of does work, but it looks a lot better in person than it does on camera.
This is when I realized that I placed the magnet holder too close to the rotational assembly, causing them to bump into each other. Meaning I had to get rid of the magnet. No big deal, because it was kind of useless anyways. And all that was left to do was program it so it could show pictures and videos. So Why don't we have a look? That's goddamn right. This was an elaborate way to rickroll you. I'm gonna build 1,000,000 more endotropes. I'm gonna build one the size of a house. It will be fully 3D. Also, I've tried my best to open source the whole ordeal. The link to my GitHub will be in the description.